So today the subject of the lecture is recursive estimation. This is a quite exciting subject, and it will provide you with, first of all, with a new tool that will allow you to learn models from data online. So you are receiving data from a plant, and you are updating your the estimation of your parameters. And then we are going to examine a number of properties of this squares estimation. Okay. So the subject of recursive estimation is presented in this slide. What you want to do is to develop an algorithm that I call RLS, so recursive least squares. So I want to modify the least squares batch algorithm that we studied yesterday in such a way that you assume that you have some estimate at time t minus 1. Okay, t is discrete time, 1, 2, 3, etc. And you have a previous estimate at time t minus 1. And you also know a number of auxiliary variables at time t minus 1. And we are going to see that the only auxiliary variables that we need is the covariance matrix P. And you receive a new data point. So you receive y of t and phi of t minus 1. So that a new data point. And you combine the new data point with the previous estimate and the previous auxiliary variables to update your estimate. So building the new estimate theta of t and auxiliary variables, new auxiliary variables p of t. Okay. Now, a word about notation. Usually I put a hat to mean that it is an estimate of the variables. Now I'm omitting the hat here to make the notation lighter, to simplify the notation. So this theta that appears here is the estimate, is to be understood as the estimate of the vector of parameters. So this is what we want, and we want to do this by modifying the batch least squares algorithm that we studied yesterday. So let's write the equations that we had in a different way. So you know that the batch least squares estimator, if you have t points, t data points, so you have been observing data for t equal to 0, 1, 2, 3, 4, etc., up to t, the general value of t. And you build this matrix phi, capital Phi, which is made of, each row of phi is a vector small phi. And you build this matrix, phi transposed phi inverse. And you do this multiplication, and you multiply by the vector of independent data y bar. Okay, now you can show by a number of manipulations. Perhaps the simplest thing is to do an example, 2-by-2 example. I won't do it, but you can do it at home. You can rewrite this formula in this other way. Okay, so this capital lambda, this is the Greek letter capital lambda, is nothing more than phi transposed phi. Okay, so I have phi transposed phi inverted, and I have then phi transposed y bar, and phi transposed y bar, you can also see, it's not difficult to see that it's made of a summation of k from 1 to t of yk phi k minus 1. Okay, and furthermore, this capital lambda matrix, which is phi transposed phi, and I told you that this matrix is the information matrix, is the inverse of the error covariance matrix. You can write phi transpose phi as the summation of matrices. You see that phi is a vector, and phi transpose is a column vector, and phi transpose is a row vector. So when you multiply a column vector by a row vector, you get a matrix. And each of these matrices has a rank 1. A característica de cada uma das matrizes phi transposto é 1. But when you start summing these matrices, you will get, hopefully, if your data is correct, you will get a matrix which is invertible. Okay, because you will have different values provided that your data excites the system. So the different phi will be independent, and so this gamma, capital lambda matrix is invertible. Okay, and this is nothing more than phi transposed phi. So do a 2x2 example to convince yourself that you can write phi transposed phi in both ways, as the product of these two matrices or as this summation. Okay, so we are going to work with these two forms for the estimate. So these two equations define the batch least squares estimator. Okay, so you compute, you have a number of data, and the data is phi and y bar, and the elements of y bar are the y case. And what you do is you compute the summation, okay, and then you compute inverse and you do this multiplication here. Now, what is the advantage of writing the batch estimator in this form? It's because you have summations of the previous data. So if you want to relate the estimate up to time t with the estimate of time t minus 1, probably one strategy would be to isolate the last term in these summations here. So let's do that. Now, I rewrote here the estimation, the formula for the least squares batch estimator, and I'm going to isolate the most recent term, so the term for k equal to t. Okay, so for k equal to t, you get yt phi t minus 1, which I wrote here, and then you have a summation from k equal to 1 up to t minus 1. Okay, so the term between square brackets is nothing more than this full summation here. Okay, but now you can write this summation here that appears up to time t minus 1 again, thinking that it yields a batch estimator but with t minus 1 point. So if you use the same formula with t replaced by t minus 1, you can say that your estimate at time t minus 1 is the inverse of lambda times this summation. So this summation is lambda of t minus 1 theta estimate of t minus 1. Okay. Here I started placing the estimate. Okay. Now you replace the summation by lambda t minus 1 theta hat at t minus 1. Okay, and you get this formula. And you get this formula. Now you have here the inverse of lambda at time t, and you have here lambda at time t minus 1. So probably one thing that you can do is to get an expression for lambda at time t, relating this with lambda at t minus 1, and then perhaps get a relation for an equation for or an expression for the inverse? No. No. So this is the formula we have deduced, and we know that lambda is something in which you are accumulated terms of the form phi transposed. Okay. So let's go back a little bit. You see? So in lambda, you are adding terms of the form phi transposed. So you can say that lambda of t is lambda of t minus 1 plus phi of t minus 1, phi transpose of t minus 1. Okay? So you are adding these terms to the previous information matrix. The new information matrix is the old one plus phi transposed in the most recent point. Okay, so I know that lambda is the previous lambda plus this term, so I have this equality here. And I can replace lambda of t minus 1 by lambda of t minus phi transpose of t minus 1. So I do this, and I got this stuff because everything here will multiply by theta of t minus 1, the estimated time t minus 1. So I get here lambda of t theta hat of t minus 1, and then minus phi transpose theta hat of t minus 1. So that's what you get here. Plus y of t phi of t minus 1. Okay? Now, when you multiply this lambda inverse of t, this will cancel this first term. So you just get theta hat of t minus 1. And then you get that lambda inverse times phi of t minus 1, phi transposed. Okay? But now, you see that I have phi, and I have y phi, but y is a scalar, so y phi is the same as phi y. So I can isolate this term here, y. I can also isolate phi transpose theta hat with a minus sign, put it here. And then the common factor is phi. You see phi here and phi here. Okay? And this lambda minus 1 that appears here. So this is nothing more than a little bit of algebra. Okay? Now, this formula has already some interest because what are we saying? We are saying, let's move to the next slide. We are saying that the new estimate is the previous estimate plus a correction. This here is a correction. You receive the new data point and you do a correction to the previous estimate to get a new estimate. Okay? And this correction is what? Look at the term between square brackets. This is y of t, and this is phi transposed at time t minus 1 times theta hat of at time t minus 1. So this is what you would expect y of t to be given your previous estimate. If the previous estimate were correct and you had no noise, then this would be 0 because this would exactly be y of t. But if you have some estimation error, then you will have some non-zero value here between as the result of the operation between the square brackets, and you modify this non-zero value by a gain. Okay, and this is a vector gain because lambda invert is a matrix and you're multiplying by a vector, so this is a vector. So you are multiplying a vector by a scalar, which is this quantity here, to correct the new estimate. Okay? So you have an algorithm which is made of these two equations. One equation that propagates the information matrix. Just says that the new information is the previous information plus the information carried on by the latest data point, 5 phi transposed. And then you invert this lambda matrix, and you do these computations. So you update your estimate by adding to the previous estimate this quantity. Okay? I call this quantity here between the square brackets the innovation. That's a new piece of information about the estimate. So I can say that the new estimate is a previous estimate plus a gain times the innovation. Okay? So this is a nice formula. But there is one thing that is probably not so nice. You figure out what it is? Há uma coisa que não é assim muito simpática nesta fórmula. Conseguem perceber qual é? Actually, it's written here. You have to invert a matrix in each iteration. Okay? Now, probably we can get rid of this inversion because we know how to propagate lambda, capital lambda, the information matrix. And you propagate in time the information matrix by adding in each step a matrix with rank 1. So probably you can take advantage of this expression for lambda and the fact that each time you are modifying your matrix only along a direction. So probably you will need only to invert one scalar. Okay, that's a heuristic. So to do this, we need okay. This is what it's a summation of what we have. We need to okay. We need to get rid of this inverse. Now, we could say, okay, let's propagate the inverse of lambda instead of propagating lambda. Because if we propagate the inverse of lambda, of the information matrix, then we don't have to invert it. And okay, remember that the inverse of the information matrix is the error covariance matrix P. So I put here P of T, and I'm inverting this formula, so I get the inverse of lambda is the inverse of this sum. So I'm saying that P, the inverse of lambda, is the inverse of all this stuff here. Okay. So here in the equation for theta hat, I don't have to invert any matrix provided I have P. But to compute P with this equation, I still depend on lambda. So I'm going to use one thing, which is the matrix inversion lemma. Okay, so I want to invert this sum of matrices, and for that I'm going to use this equality. The equality is this one. If you want to invert the sum of A plus B, C, D, and A, B, C, and D are matrices with computable dimensions. Okay. That's the only thing that I ask. So A must be squared, and the product BCD must be squared of the same dimension of A. This imposes constraints on the dimensions of B, C, and D. Now, provided that the inverse of A exists, you have this expression. Now, how can we prove this expression? It's a question to you. It looks quite complicated, but how do you prove that one matrix is the inverse of another matrix?
You can invert it again and see if you end up with the original matrix.
You can do what?
You can invert it again.
Okay, so I could try to invert this, and prove that this gives me that, but
Or you can
even
multiply
more
them
complicated. Yes?
Or you can multiply them both and they will yield the identity matrix.
That's right. That's much simpler. So you multiply this expression here by A plus BCD. Okay? And the result is the identity. And you have to do it on the left and on the right. Okay, remember that. So after some algebra, you can prove it. It's an exercise on matrices. So I'm going to use this result. I'm going to use this result. Now, what I'm going to say is that A will be lambda. That is to say, A minus 1 is the inverse of lambda, so it's P. B is phi, C is 1, and D is phi transposed. Okay? So what do I get? I get here that the inverse of A is lambda, plus B is phi, C is 1, phi transpose is D, okay, is A minus 1. A minus 1 is P. Minus P, B is what? Phi. Then I have the inverse of D, A minus 1, B. So D, phi transposed, A minus 1, P, and B is phi, plus the inverse of C, which is 1. So then I invert it. And then I have D. D is phi transposed, A minus 1, which is P. Now, I observe that this is a scalar because this is a product of a row vector times a matrix times a column vector. If I do the product of a matrix times a square matrix times a column vector, I get a column vector. Row vector times a column vector gives a scalar. Okay? It should be because here I'm adding it to 1. So I'm just dividing, this inverse is just dividing by the scalar. So I can rewrite this formula simply as P phi transpose P divided by the scalar. And I get these equations, okay? So in this way, we get the recursive least squares algorithm, RLS. And what is the model? We are estimating the true parameter vectors, theta naught here. Y and phi is made of data, so I can observe Y and phi. E is some noise. And so how do I propagate my estimates? I have to compute this formula that says that the new estimate is the previous estimate plus some gain. This gain is the Kalman, the so-called Kalman gain, times the innovation. So this is the difference between what you observe for Y and what you are expecting Y to be given your previous estimate. Okay? And K is P phi, and P satisfies this equation that came actually from the matrix inversion lemma. Okay, so actually the order, if you program this algorithm, you start by the expression for P, this last one, then you compute K from P, and then you compute the update of the estimate using this equation here. Okay, this first equation is here just to remind you what is the model for which we are estimating parameters. It does not enter the algorithm. You don't know theta naught. Okay. Some of you probably have heard about the Kalman filter. Actually, this is a special case of the Kalman filter. Okay, that's why I call this the Kalman gain. It's not just myself; it's a common usage to call this the Kalman gain because it's a Kalman gain. The filter, the Kalman filter, is a way of estimating. It's a way of estimating the state of a system, of a linear system, and you actually say that the new state is a previous state times time plus a gain times some output error. Okay, and you can rewrite the problem of estimating the parameters in such a way that it becomes a state estimation problem. Later, when we speak about control based on state space models, we will say a little bit more about it. For the moment, this is just one name, Kalman gain. Remember, Rudolf Kalman is worth being remembered. Although he was a very complicated guy in personal terms, okay, but he is one of the main researchers of electrical and computing engineering. Okay, so we have this. We can also rewrite these equations in this other form. Okay, so this is just picking up the expression for P given by this equation for P is the so-called Riccati equation. So you pick up the Riccati equation, plug it there, and use the definition of K in the Riccati equation also. And you have two equivalent expressions. Okay, so sometimes the equations for the recursive least squares algorithm are also written using these two expressions. The first equation is the same in both cases. Any question up to now? So the recursive least squares algorithm operates in this way. You want to estimate theta naught in this model, and you are observing y and phi. And what you do, you update this error matrix, error covariance matrix, sorry, P, by using the Riccati equation. Then you compute the Kalman gain, and then you update the theta in this way. Okay. Now, suppose that, well, the first thing is that you need some initial estimate. What could be an initial estimate here? Remember that P is actually proportional to the parameter estimation error covariance. Okay? The proportionality is the noise level, so it's the noise variance. So usually I say that P is the error covariance matrix. Estimation error covariance matrix. So how can I initialize my parameters, my algorithm? Because I need an initial P. Well, K is computed from P, so I don't need to initialize it. But I need also an initial estimate. So what do you think? Suppose that you know nothing about theta naught. If you know nothing about theta naught, then you assume a value, and you can say, well, theta naught is 0, 0, 0, 0. It's a vector of zeros, or a vector of ones, or a vector of random vector, okay, whatever. So you are committing a big error. So one possibility is that you select theta to be, the initial estimate of theta to be anything you want. And since you have a big initial error, the covariance matrix must be a big one. So try to use P as a diagonal of large numbers, say 1,000, okay? And then you start receiving data, and hopefully it will converge. Actually, the conditions for convergence are quite mild. I mean, in many cases, this algorithm will converge to the true parameters, provided that they exist, and provided that the noise is white. Remember that if the noise is not white, it won't converge to that. Or it will at least converge to the best approximation. Suppose that you have you are assuming an order for the system which is smaller than, then it will converge to a local minimum. Can happen. Okay. Now another question is this: suppose that you know nothing about what I've been speaking about in the past half an hour, and you want to write an estimation algorithm which is recursive, So this structure here of this equation is plausible. It says the new estimate is the previous estimate plus some correction. And it's reasonable to assume that the correction is something that depends on your capacity to estimate y of t, the output that you are observing. So you put here just some gain. Okay. Now, if you put here some gain, a small one, if the gain here is a constant, but a small constant, these corrections will be smaller. So if things converge, they will converge slowly, because each time you have an error, you are multiplying it by a small number. So you probably converge slowly to the true value. If you want to increase the speed of convergence, what would you do? Tem um algoritmo que é a nova estimativa é a estimativa anterior mais um ganho vezes o erro à saída. E agora põe aqui um ganho pequenino para esta correção ser pequena. Isto, vamos supor que ia convergir para o valor correto, mas ia convergir lentamente porque o ganho era pequeno. Se quiserem acelerar a taxa de convergência, o que é que podem fazer? No ideas?
Maybe increase the gain.
Maybe increase the gain. Okay. If you increase the gain and you have some noise, so imagine that you have some noise. Do you think can you have very, very large gains, or you can expect problems? What type of problems can you expect if you start increasing the gain?
It may not converge.
It could not converge. Well, it could not converge, but assume that it converges. But then what happens? Suppose that you have noise, okay? And suppose that you are lucky and you selected as an initial estimate the true value of the parameters. Does the new estimate becomes equal to this true value of the parameters? So you start, your estimate at some time becomes the true value of the parameters. And then you iterate this algorithm. Does the new estimate is still the true value of the parameters?
No.
No, okay, tell me.
Because of the error.
Because of the noise, no? Okay.
Yes.
So what happens? Can you explain it a little bit better?
I think so. So both thetas are equal, but the expression still has that noise. So it's going to jump out of the optimal position by that noise amount.
And
if the K is big, then it's going to be a big jump and it's going to be far away from the optimal position.
Very well, thank you. That's perfect. You see?
You're welcome.
So if k is small, it takes a lot of time to converge. If k is big, it converges much faster because small errors in the output cause a lot of action to update the estimate. But then your estimate in steady state will have a larger error because it's going up and down and up and down. And this is just noise. You are not really using any new information. So what could we do with k? Instead of using a constant k, could we use what?
Maybe an adaptive k that is going to be smaller as theta's are closing in.
Yes, okay, that's the idea, okay? Now, let's see a simulation. Let's see a simulation. So in this simulation, I just have, my model is very simple, okay? So phi is just some signal. I think it's white noise, but it's some signal that I know. And I want to estimate this parameter, which is 2, as the value 2. And I add some noise. So I want to estimate theta naught. The true value is 2, but I know it because it's a simulation. In practice, you never know the parameter you are estimating. And I add this random error, which has a 0 average. And you can see that with a fixed gain, you have this green line here. It converges slowly to the true value of 2, and then stays there more or less, fluctuating very little. Now, if you increase the gain, here we had 0.03. Now I have a gain of 0.5, so more than 10 times. It converges much faster, but then it becomes very sensitive to the noise, and it becomes amplifying a lot the noise, okay? Instead, the least squares you see is the best of two worlds. The least squares is doing in an automatic way this idea of starting with a large gain because P is large. So you converge very fast. Actually, much faster even with this high gain of 0.5. And then it stays almost constant. You see, the blue line. That's the common estimator, the optimal least squares estimator. Okay? Let's look at what is happening to P. This is the code if you want to replicate this experience in MATLAB. It's very simple. Now, look at what is happening in P. I started with a P which was 10 to 3, but I'm not showing it. So it decreases very fast, okay? And then it becomes very small. This is a logarithmic scale in the vertical. So the algorithm is learning. Learning means that is receiving information and P is decreasing and the algorithm is converging, okay? So what happens in this algorithm is that you should start, if you know nothing about theta naught, you should start with any value of theta, okay, at any value of the estimate, and a P which is a large matrix, usually a diagonal of large values, typically 1000. Okay? And now, when you are operating the system, you receive more data, and P is decreasing. I mean, P is a matrix, but think of the trace of P, for instance. Okay. When I say P is decreasing, means the trace. The trace is a sum of the parameter errors or squared. So of the standard deviations of the parameter errors. So P is decreasing, okay? And when P decreases, the common gain decreases because it's proportional to P. And this term is decreasing. So theta, the estimated time t becomes closer and closer to the estimated time t minus 1. Okay. Now, p is decreasing because your data is informative. If the data is not informative, then probably you are just adding information along some directions of the space of parameters. And what happens is that some of the components of P decrease, but others do not decrease. And if they do not decrease, then you do not converge. And some parameters may converge and some other parameters may not converge. Okay, now, before going on, so this is the situation when you know nothing about the parameters. Suppose that you know something about the parameters. What would you do? Suppose that you have some reasonable estimate of theta naught, and but you want to improve it by receiving more data. So what would be a wise initialization?
The information we already got.
So how do you select the initial value for theta and the initial value for p?
Since you were saying that we already have a notion of the conditions of theta, we can use that as the initial condition, and then we can have a P matrix with some lower values.
Okay, that's right. That's correct. So P could be the diagonal of smaller values. Okay, that's the standard deviations of the error that if we have some notion of that. Actually, it's usually you do an experiment and you have an estimate of theta naught, and you also have some last value for P, because you have been working in today and tomorrow. When you start, what you do, you, instead of using a diagonal P with small values, you put the last P that you had. Remember that P is decreasing. This is much better in practice. If you have full information from a previous experiment, don't use just the last estimate, but also use also the estimate from the last value of P. Okay, that's quite important, because this equation, you see, it has some geometry, and if you are respecting that geometry using a P from the last experiment, you are respecting the cross correlation between the different parameters. Okay, in practice, so it's much better. Actually, I had a rich experience, personal experience, in using these algorithms with adaptive control. In adaptive control, you use these online estimators, and you update the gains, you redesign your controller online. Okay? That's adaptive control. And I was doing one experiment, for instance, controlling the temperature of a solar field, of solar collector field. And the first experiment we did, there was very strong transients, because there were initial some transients about the estimate, but it converged. So we saved the data, and when we restarted, we came the next time to do experiments. We were using the last estimate and the last value of P, and by using that, we were avoiding this learning or adaptation to initial transient. Any question? Okay, so we have this thing, and remember that learning is reducing the error. I mean, you learn about something when learning is not just to get an estimate, is to get an estimate for which the error covariance is small. you can see here in the cases of linear models, of course, you can apply least squares to nonlinear problems. In that case, you don't have this very nice recursive formulas, but you can still do the estimate with least squares, parameter estimation with least squares. But what you are doing is making a Gaussian assumption. Okay, so you are characterizing your parameters by a Gaussian density, and you are somehow estimating this Gaussian density. So you start, you see, this is the horizontal axis is made of values for the parameter in this example, in which you have just one parameter. Now I start with a large covariance. A large covariance is a widespread Gaussian density, because if the covariance is very large, so the density, the Gaussian density associated, I was using 0 mean value and a large covariance value. So it's something which is very widespread, going to 0 in this side and symmetric to the negative side. Now, after 200 observations, I look at a Gaussian, which has a mean value, which is my estimate, and my estimate, you see, is quite close to 2. And the covariance, the variance parameter of the Gaussian is the P matrix. Okay, and I plot it here, and you see that your ambiguity has been much reduced. Okay, so think of learning in terms of probability density functions. And when you are learning, you are squeezing your the probability density function that describes the knowledge that you have about parameter. You are squeezing it by learning around the true value. Okay. Another example. Remember this example in which I had a system in which the output is just the weighted sum of the last 2 values of the input plus some noise. Okay? And I start with some initial information. Okay? So I put some initial information, and then I receive data, and I update that. Actually, you remember Bayes' law. Actually, we could derive these equations, the equations for least squares, by assuming that everything is a Gaussian and propagating the mean value and the variance of these Gaussian functions using Bayes' law, okay, for conditioned probabilities, because what you are computing is the probability density function of the parameter given the observation. Okay? So you start with some initial estimate, and the initial estimate means an initial value that I assume to be 0, and also or 1. I think it was 1. I can't remember very well. It was not 0. But anyway, it was some value, and with some p. Now, in this case, I have 2 parameters, b0 and b1. So my functions are 2-dimensional. Okay, they exist in a 2-dimensional plane, and the probability density function exists, of course, in a 3-dimensional space. Now, what happens? Suppose that u is constant. So I can estimate the I cannot estimate both simultaneously the sum and the difference of the parameters. Okay, that is why. Because I can't, if u is constant, I only can estimate b0 plus b1. Okay? If I could estimate the difference of the parameters, in that case, I would have the sum and the difference. I could find the parameters, but that's not possible. So what happens? I start with a Gaussian whose level curves are circumferences. Okay, and then I do a number of observations, a few observations, and I'm squeezing the density in this direction. You see here in the plot in this direction. That corresponds to the sum, but in this direction, which is orthogonal, that corresponds to the difference. I'm just saying the same with the initial observations I had. Okay, so there is no miracles. Okay, you run the algorithm, you get more data, and this is squeezing in this direction, but keeping the same spread in the orthogonal direction. Okay? So when you have parameters that are not identifiable, usually it's a function of the parameters that are identifiable and some function that is identifiable. In this case, the difference of the parameters is not identifiable. The sum is identifiable. You can estimate b0 plus b1. Then there are some directions along which p is decreasing. And along the orthogonal, the not identifiable directions, it stays the same. Any question? Okay. So we have this problem of unidentifiable parameters. So let me give you another example. And this example is related to control. Suppose that you have this system, okay, in which A and B are parameters, and E is noise. And you select your U, and you observe Y and U. Now, use a very simple controller, just a gain minus K that multiplies the output to build U. Okay? So U and Y are bound by this equation, and you can multiply everything by a parameter beta that is constant and it's not zero, and you get an initial condition, an equivalent condition satisfied by U and Y. So for any beta that you place, U and Y are related by this equation here. Now, since this is zero, you can add up these to both sides of this equation. So you add 0 to Y and you get Y, and you get beta U plus beta KY to the right term, and you get this stuff here. So from here, you see that your model satisfies not only the open loop model. If you look at Y and U, you are not just, if you have pairs of Y and U, you are not just, you have a record of values for U and Y that satisfy not only the open loop model, but also this family of models. And this, whatever beta you place here, you get a different model. Okay? So if you apply least squares to estimate Y, to estimate the parameters that multiply Y of t minus 1 and U of t minus 1, you are not going to get the true value of A and the true value of B, but instead anything that is like A plus BK and B plus beta. A plus beta K and A, B plus beta. So this means that if you, your estimates are given by this, If you eliminate beta, you know that your B estimate and your A estimate are related by this value, by this expression here. Okay, that is to say, when you do an estimate, you will converge to some point, any point in this straight line of slope 1 divided by the gain of the controller. And this slope passes by the true value of the parameters. You may converge to the true value of the parameters, but you may converge also to another point, provided that it is in this line. Okay? And you can even slide. Usually what happens is that your estimates, they slide. They are here, then they are here, then they are here, then they return, then they come here, they are sliding, okay? Like swinging, like you are in a ball. É como se estivessem a dançar, like you are dancing, okay? To a couple dancing, it's like the estimates of A and B, okay? So this is something that appears very often in adaptive control. You must be careful. Now, suppose, and it's undesirable because you can have divisions by 0. Suppose that one of the estimates goes to 0 and you are dividing by that estimate. It's undesirable. So we want to avoid this situation. And what can we do? I accept ideas. What can I do to avoid this unidentifiability problem? The problem comes because I have a constant k, and the constant k yields this relationship between u and y. So what could I do?
Maybe remove the controller.
Okay, maybe I could remove the controller, but sometimes I need to have the controller because I want to have the controller there. And I don't want my estimates to swing. Okay, usually this type of things happen because you are estimating the parameters of the plant, and somehow, this is not shown here, you optimize k based on these estimates. That's adaptive control. So you are doing control because you want to do control. You want to keep the system still. But then you have this problem of the k swing. So making k equal to 0 is not an option here. Other options. What do you do if you have a bad estimate? This is an estimate because you have a tight relationship between data, u and y. Okay? So what is the remedy when you have bad or poor estimates due to poor data? Shake the system. Okay? So how can I shake the system? Deviate it from this, break this condition. How can I do that? For instance, I could use some disturbance in k. I could add some deviation of k to the optimal one, at least in some periods of time. Or I could use, instead of having just u equal to minus ky, I could use some jitter. Jitter noise means ruído de agitação. I could hear some signal of very small amplitude, but that's enough to avoid that this relationship holds, and so the parameters would converge. So whenever you have identifiability problems, you need either to reduce the number of parameters that you have, and above all, to have a better excitation of your system. So the trick here is usually to add some signal. Okay? Now, this controller is a controller that regulates the state to 0. If you want to bring your y to some value which is non-zero, okay, to track a reference, then the reference can itself impose some excitation on the system. And you can use the reference as this extra excitation to avoid these identifiability problems. Any question? Okay. So I think I will start here. We have learned a lot of things today. So we solved the problem of recursive estimation for least squares. And I tried to explain to you the mechanism of, let's put here the equations once again. The mechanism of convergence of the estimate. So what happens is that the data comes. If the data is rich enough, then the covariance matrix decreases. By decreasing, the Kalman gain decreases too, because it's proportional to P. And this term decreases, the correction decreases, and theta at time t becomes closer and closer to the estimate at time t minus 1. Okay? Remember this stuff. Any question? Any final question on the lecture? So have a good week of work, and we'll see each other on the next Monday. Bye-bye.
Thank you, Professor. Bye.
Bye, Professor.
Thank you. Bye.